Hello, today we're continuing in our series on nuclear physics, looking at nuclear fission reactor principles. Last time we established that uranium-235 is fissile. By that we mean that it can capture a thermal, that is a slow-moving neutron with very small amounts of energy. It captures the neutron to become uranium-236, but that uranium-236 will be in excited state. And that excited state is sufficient to get over the activation energy barrier in order to fission into two nuclei, X and Y. That could be a variety of different numbers, but X is usually round about A is 140 and Y is round about A is 95, plus some neutrons, depending on exactly what X and Y are, plus energy. And you'll recall that we said that if you plot the mass energy of the large uranium-235 as against the mass energy of the two nuclei X and Y, the mass energy of the uranium-235 is greater than the total mass energy of the two nuclei X and Y, and you would expect therefore that nature would simply roll down the hill. But in fact, in order to do that, the nucleus must first distort, and in distorting, its surface area increases, and that effectively means its mass energy increases, and so there becomes a barrier. And the height of that barrier is called the activation energy. And in the case of this reaction, you need an activation energy of about 6.2 MeV. And where is nature to get that from? The answer is it is in the potential energy, in the excited state of the uranium-236. And that gets it over the barrier and therefore can fission. We said that if it were a uranium-238, which is by far the most abundant isotope, then the 238 will indeed absorb a neutron and become uranium-239, but the energy, the potential energy there is only 4.8 MeV, and that won't get over the barrier, which is still about 6.2 MeV. And that's the reason that uranium-238 does not readily fission by absorbing a neutron. So here we have the basis of fuel for a nuclear reactor. We take our uranium-235, which is a very small part, 0.7% of natural uranium. The rest is pretty much uranium-238, which isn't fissionable, sadly. But uranium-235 is. We could enrich it to about 3%. We allow it to break up into X and Y, neutrons and energy, which will now be in the form of heat, because although this energy in the uranium-236 is potential energy, by the time you get here, the energy will be in the form of kinetic energy, because although the total momentum will equal zero, because the neutron's got virtually no momentum, this uranium has none, therefore this has none, that's why it has no kinetic energy, it only has potential energy. But now you can still have a total momentum equal to zero because they all fly off in opposite directions. But they will have momentum and they will have therefore energy, which is kinetic energy, is p squared over 2m. So these will have energy, and as we learnt with alpha and beta particles, the smaller the particle, the greater the proportion of the energy that it carries off. So most of the energy gets carried off by the neutrons, and that neutron can be, that kinetic energy can produce heat, which is another form of energy. That's the energy here, and that can produce steam, and that can drive a turbine, that can turn a generator, that can produce electricity. So that's the principle. So we need to draw our ideal design for a nuclear reactor. So we're going to need some kind of lead-lined, concrete-lined box, because let us remember that this produces radioactive material. X and Y will beta decay to produce more elements, and that is radioactivity. So it's radioactive, we need to protect the workers, so this is going to be lead-lined, concrete-lined, and inside we will place our uranium rods. They will be a mixture of uranium-238 and uranium-235, of which of course only 235 is going to do the fission work for us and produce the heat that we need. And we better have a coolant in the tank And for want of anything else, let's go somewhere cheap. Let's have water, H2O. We pump the water in and we take the water out. In here it's going to come in cold, and then when you've got this energy coming out of the nuclear reaction, that's going to produce heat, that's going to warm up the water, and you're going to get hot water or steam coming out. And we'll sort out how we deal with that later on through some form of heat exchanger maybe. So we put it through a heat exchanger, and then when it's cold it can go back in at the bottom again. So that basically is the principle of our nuclear reactor. But there are two issues that we have to address. The first is that these neutrons are fast-moving neutrons, right? They carry away MeV worth of energy. These neutrons are thermal neutrons. They've hardly any energy at all. When that neutron is absorbed, it's gone. These are the neutrons that can go round the loop again and hit another uranium-235 to make a uranium-236. So these are the neutrons that are going to allow this process to keep iterating. Because every time you go through the process, your neutron is absorbed, but you produce new neutrons and they can go round the path again. So every iteration absorbs a neutron, but produces fresh neutrons. The trouble is you need thermal neutrons. If they're too fast, it's much less likely that the uranium can capture them. We saw that in the last video. The cross-section for a low energy neutron is much higher than the cross-section for a high energy neutron. So these need to be low energy neutrons. At the moment they are high energy. And the second problem we have is that there are N of them. And depending on what X and Y you get, the average value of N is 2.5. So for every neutron you have, each iteration produces 2.5. If you just allow that to keep flowing, very soon you will have a huge amount of reactions going on, a huge amount of energy being produced, and that will just go boom. That is a nuclear bomb waiting to happen. Really, N should equal 1. If you can get N down to 1, then every iteration uses a neutron and produces a neutron. But at the moment, N is going to be of the order of 2.5, depending on what particular elements X and Y are produced. So two problems. There are too many of these neutrons, and they're going too fast. Well, let's deal with slowing them down first. How do you slow something down in classical mechanics? Think of two billiard balls or snooker balls on a table. This is still, indeed this is still, but you hit this with your snooker or your billiard cue. You hit it, it runs along the table and hits this stationary snooker ball, and what happens? This one stops and this one shoots off with the same velocity that this one had. This one stops because it transfers all its momentum and all its energy to this one. Now we don't necessarily want to stop the neutron, we just want to slow it down. So the same principle applies. You take your neutron, which has a mass little m, and let's say it has a velocity v, which is going to be fast because it's a high energy neutron, and we collide it with something which will have mass capital M, and initially its velocity is going to be 0. And that is going to produce a situation where the neutron is traveling, which has a mass little m, is going to be traveling at speed v1, which we want to be slow because we want it to be a thermal neutron, and the object we smashed it against, the capital M, will now be travelling at v2. So this is classical mechanics. We smash a neutron against a stationary object, then the neutron is travelling very slowly and the neutral object is travelling with speed v2. We can write two equations here. The first is conservation of momentum. Momentum will be conserved before and after the collision. So the momentum before the collision is simply m little mv, because this has v equals 0, so there's no momentum here. And that's going to equal the momentum after the collision, let me make that clear, equals mv1, which is the momentum here, plus capital MV2, which is the momentum here. We can also say that kinetic energy is conserved because we're going to make the assumption that there is no, as it were, potential energy, there's no excited states, there's no noise, there's no light, there's no heat generated, it's just energy conservation within subatomic particles. So the energy on this side is going to be a half mv squared. No energy here because v is 0. And that's going to equal a half mv1 squared, that's here, and a half, so plus a half capital M V2 squared here. So those are the conservations. This is conservation of momentum, equation 1. This is conservation of kinetic energy, equation 2. You can see that I can cancel out the halves because there are halves throughout. And now what I'm going to do is to rewrite those equations in terms of V2. So let's start with the top one. V2 is going to equal, well, bring this round here, you've got m into v minus v1, and then you've got to divide by m, so that's m over capital M. That's v2 from equation 1. And similarly from equation 2, I've got that v2 squared here is equal to m into v squared minus v1 squared. And then I've got that m there, so I've got to divide both sides by m, I get m. So v2 squared is m over capital M, v squared minus v1 squared. But v2 squared is also equal to this term squared. So that's going to be m squared over capital M squared into v minus v1 all squared. We've simply squared both sides here. This then becomes v2 squared, which is this. So this equals this. And you can see immediately that I can cancel one of the m's there and one of the capital M's there. And now I can rewrite that equation by bringing the m up to this side as, and multiply through mv squared minus capital M v1 squared. So I've taken the m up to here and multiplied by those two. And that's going to equal, I've still got one m left here, m into v minus v1 squared. If I here take the m on the outside, so I've got m into v squared minus v1 squared, that of course is simply v minus v1 into v plus v1. That will give you v squared minus v1 squared equals m into v minus v1 all squared. And now you can see that one of the v minus v1s cancels. So that cancels and one of the squared terms cancels. Now I can multiply through and I have mv plus mv1 is mv minus, that's little m minus mv1. Now I want to rearrange in terms of v1. So I've got v1 into m plus, bring this over this side, plus m equals v into m minus capital M, bringing this onto this side. So I've just rearranged this formula in terms of v1 and v. And now I write v1, divide both sides by m plus m. I get v1 equals v into m minus m over m plus m. And then I ask myself the question, if v is large, which it is because that's the initial speed of the high energy neutron, and I want v1 to be small, what does this fraction have to be? And the answer is, of course, it has to be very small, a small fraction. And how do you get a small fraction here? You have m very similar to capital M. If m is almost capital M, then m minus m is a very small number, but m plus m is going to be a much larger number, so the fraction is very small, and you effectively take a very large V, the high energy neutron that comes out of the nuclear fission reaction, and you slow it down to a thermal neutron. That's the idea. So we want something that is broadly the same mass as a neutron, so that we can smash the neutron into it, give up the neutron's energy and convert it to a thermal neutron. And what do we know that is very similar to a neutron in mass? Answer, a proton. And where do we find protons? Answer, they are the very core of hydrogen. Hydrogen has a proton and an orbiting electron. And where do we find hydrogen? In water. So by an incredibly happy coincidence, not only can that water be used to carry the heat away that is generated by the fission reaction, but it also contains hydrogen, which contains protons, and those protons are the very things that the neutrons can smash into to slow the neutrons down so they become thermal neutrons, so they can go round the iteration again. So the water is not only a coolant, it's also called a moderator. It slows down the neutrons and makes them thermal neutrons so they can go back into the uranium fuel and cause another round of uranium fissioning. Okay, that's dealt with the first of our problems, which is, let me just move that across, save me rewriting it, which is that these neutrons are too fast and they have to be slowed down so that when you've got these neutrons going through the system again, they've got the right cross-section to be absorbed, they've got the right energy to be absorbed by uranium-235 to produce uranium-236. The second problem, however, was the more serious one, that N is about 2.5, which means we've got too many neutrons, which means if you just let this process iterate, you will very quickly, and we'll see why in a minute, you'll see why we get to a very large and an unstable position. It becomes a bomb and it goes boom. So we've got to get N down to 1, and at the moment it's 2.5. So how do we do that? Well, nature will assist us initially. So our problem is that we produce N neutrons for every iteration, where N is approximately 2.5, and we want to get that down to 1. So how does nature assist us? Well, the first thing is that when the neutrons, the fast neutrons, are produced in the uranium rods, there is a possibility that some of them will be absorbed, but without fissioning. Because you'll remember I said that whether it's uranium-235 or uranium-238, the uranium-235, for example, can absorb a neutron. So here's uranium-235 plus a neutron becomes uranium-236 in an excited state. So this is the ground state, here is the excited state. And then we said the potential energy in this excited state has sufficient energy to get over the activation energy barrier. But if it were 238, it wouldn't. So what would happen in the case of uranium-238 that goes to its excited state? It would simply fall back to the ground state and emit a gamma photon. So the neutron would be absorbed, but without producing any more neutrons. It hasn't fissioned in uranium-238. Consequently, all that happens is the uranium gets absorbed, pushes uranium-239 into an excited state. That then de-excites. The neutron is still there. It hasn't been released. All that's been released is a gamma photon. That's no use to you. You've lost a neutron. One of the fast neutrons has been absorbed by uranium-238 to no good effect. And the proportion of neutrons that survive being absorbed is called eta. And so N neutrons originally produced becomes N times eta, where eta is less than 1. Eta is the fraction which survives not being absorbed in the uranium-238. However, I did say that there is a prospect that if this were uranium-238, ordinarily a thermal neutron would not cause it to fission, because the potential energy in uranium-239 isn't sufficient to get over the activation energy. But if this neutron is a fast neutron with sufficient energy, then it is possible, much less likely, but possible, that it can cause the uranium-238 to fission. It's a much lower probability, and we saw that in the last video, but it could happen. And if that happens, then you are going to produce more neutrons. And that factor is factor epsilon. So what we say is eta is the proportion of neutrons that survive not being absorbed. But epsilon is the proportion of neutrons that are produced by virtue of the fact that fast-moving neutrons can hit uranium-238 and cause it to fission, because the combined energy of the excited state of uranium-239 in this case, plus the energy, the high energy of the neutron is sufficient to get over the barrier. So you can get some fissioning, not much, but you can get some, and that will produce extra neutrons. And the proportion of additional neutrons you get is this factor epsilon. And if I redraw the diagram that I drew in the last video, which purports to show the cross-section, which essentially is a probability, versus the energy of the neutron in EV, and you may recall that these were log scale, so every grade is 10 times higher than the one before. What we showed was that the cross-section falls quite dramatically for uranium-235, and then it sort of tails off. So that for slow-moving neutrons, the cross-section is very high. For fast-moving neutrons, the cross-section is very low, which is why the fission reaction happens much more frequently when you have slow-moving neutrons for uranium-235. But we also said that for uranium-238, the cross-section looks like this. There is no prospect of getting fissioning for low-energy neutrons, but when the energy increases enough, then it is possible that you may prompt some fissioning of uranium-238, and that is what is producing this epsilon factor. Well, now there's a third factor, and that is that when you get to between the range of 1 and 100 eV for your neutrons, so the neutrons come out of the uranium, they interact with the protons in the water and slow down. If they get into the range 1 to 100 eV, then that is a range where you get particular resonance, and I should have actually drawn that in the graph as a series of wiggly lines. What that means is there is a particular propensity for uranium to absorb neutrons in that energy range and take them out of the system. And that is called the factor P. So P is the proportion that survive this absorption effect, which is taking neutrons out of the system. And the final factor is the factor F. What that says is that when the neutron hits water, and what of course is the neutron is going to, we hope, be slowed down by hitting the proton in the water, one of the things hydrogen can do, of course, is to absorb the neutron, to become deuterium. And there is a cross-section, a probability that that will happen. Instead of the neutron being slowed down, which is what you want to happen, it actually gets absorbed by the hydrogen. So hydrogen goes from being one proton and no neutrons to one proton and one neutron, which is deuteron. So effectively, water becomes what's known as heavy water. And for that reason, some nuclear reactors will use heavy water as the coolant, because the probability of a neutron, of course you can still have the situation where a neutron hits the deuterium and becomes tritium, but that probability is much less. So you can use water, but you will lose some neutrons as a consequence of the hydrogen simply absorbing them to become deuterons, rather than simply slowing the neutrons down. And the factor that survived that is this factor F here. So to recap, you start with n neutrons, which we said is about 2.5. And then you've got what's called a 4-factor formula, which reduces overall that total number. Eta is the proportion that survives the fast neutrons being absorbed into uranium-238 to no good effect. Epsilon is a factor greater than 1, because that represents the fact that some fast neutrons can cause uranium-238 to fission. P is the effect that you get when the neutrons slow to between 1 and 100 electron volts. They are particularly susceptible to being absorbed in uranium-235. And F recognises the fact that some neutrons will be absorbed in the water itself to become heavy water. And so each of these factors is essentially the survival factor. Eta is the survival of absorption. Epsilon represents the number of additional neutrons you get through uranium-238 fission. P is the proportion that survive this resonance effect. And F is the proportion that survive the absorption into water. And so you will get down to a value which is K. K is the consequence of all these four factors multiplying by n. And the question is K equal to 1? And does it matter if it isn't? Well, let's suppose that K, which of course is the number of neutrons you've got after all of nature has taken them out of the system for you, let's suppose that K is 1 plus delta, where delta is a small amount. I'm going to, for my example, use delta equals 0.01. In other words, we get it 1% wrong. Instead of being 1, it's 1.01. The next thing we have to ask is, how long does it take for each iteration? Because we absorb a neutron, we produce a neutron. Well, we actually produce several neutrons. But how long does it take before they go around the system again? Well, the actual fissioning, the production of these neutrons, is very fast indeed. That's 10 to the minus 12 seconds. But before the emerging neutron can go round this loop again, it has to slow down. It has to go out into the water, hit the water molecules, hit the protons, slow down, become thermal neutrons, and then it can go through the process again. And that takes about 10 to the minus 3 seconds, 1 millisecond. And we'll call that tau. Tau is the iteration time, 0.001 or 10 to the minus 3 seconds. And we'll let this process run for t seconds, which means that there will be t divided by tau iterations. All right, if there's t seconds and each iteration takes tau seconds, there will be t over tau iterations. And every iteration produces or increases the number of neutrons by a factor of 1 plus delta, because that's the whole point. So the number of neutrons you will have after the time t is equal to the number of neutrons you had at time t equals 0 times 1 plus delta to the t over tau. Right, 1 plus delta to the number of iterations. If there were 2 iterations, it would be 1 plus delta squared. If there were 3 iterations, 1 plus delta cubed. There are t over tau iterations, so it's 1 plus delta to the t over tau. Now we can take the log on both sides of that, log to the base e, so we get log of nt is equal to the log of n0. Bring the t over tau down, t over tau times the log of 1 plus delta. And if delta is small, which it is, then log 1 plus delta will simply reduce to delta. And so we've left with log of nt, that's the log of the number after time t of neutrons, is equal to the log of the number that you started with times t delta over tau. Now we can essentially anti-log that, so that nt is equal to n0, and then this of course just goes up as an exponential, e to the t delta over tau. Well, what is that? Let's let t equal 1 second. So just in 1 second, that's going to be n at time t0 times e to the t is 1 second. Delta, I told you, was 0.1, so that's 10 to the minus 2. So it's 1 times 10 to the minus 2 divided by tau, and we said that tau was 10 to the minus 3 seconds. So that's going to be divided by 10 to the minus 3. And that is equal to n at time 0, e to the 10. And that is equal to n at time 0, e to the 10 is 22,026. So roughly 22,000. So every second the number of neutrons multiplies by 22,000. So after 1 second you have 22,000 times the number you started with. And in another second you'll have 22,000 times 22,000. So you can see that the number of neutrons and therefore the number of reactions is going to increase exponentially, because for every neutron this process can occur and this amount of energy can be produced. So after 1 second you're producing 22,000 times more energy than you did at the start, and after 2 seconds you're producing 22,000 times 22,000 times more energy than you did at the start. That's why it goes boom, and it's going to go boom very quickly in a matter of a few seconds if you are even wrong by 1% with the value of K. So if we are not careful, this is going to blow up. How then do we solve the problem? We introduce what are called control rods. These are rods usually made out of cadmium, which are great absorbers of neutrons. And we lower them on our kind of hydraulic system between the uranium fuel rods, and they take out the excess neutrons so that we can get that K factor down to 1. If it's slightly more than 1, then the thing will blow up. If it's slightly smaller than 1, then it exponentially decreases and the whole reaction stops in a few seconds. So if it's slightly more than 1, it exponentially increases. If it's slightly less than 1, it exponentially decreases. You need K to be equal to 1, and you do that by dropping the cadmium absorber rods that absorb neutrons so that you get them to a position where you've just got the right amount to maintain a steady reaction. But we're still not wholly out of the woods, because you see, if this is on some kind of hydraulic basis, some motor, it's going to take a few seconds for those control rods to get into position so that you've got them exactly balancing the production of the neutrons. And those few seconds could be critical. And critical is the operative word. Because if K is equal to 1, which is what we want, that is called critical. If K is less than 1, that is called subcritical, and the reaction will stop in a few seconds. If K is greater than 1, that is called supercritical, and the whole thing becomes unwieldy. It goes boom. So we need K to equal 1. But how can we do that when the control rods take a few seconds to get into place? Well, I remind you of something we learned in the last video, and that is that when the uranium-236 in an excited state decays to X plus Y, which might be a variety of different elements, but usually around A equals 140 and A equals 95, plus of course the neutrons plus the energy. In some cases, well in pretty much all cases, these X and Y will be radioactive and will decay by beta decay. So this decays by beta decay to, let's call it P. I don't mean potassium, I just mean a product P. But in some cases that might then decay to P prime by neutron emission. So it just becomes an isotope of P by giving up a neutron. And we said that these neutrons, which are produced directly as a consequence of the fission, were called prompt neutrons. But these neutrons are called delayed neutrons because you have to wait until X has first decayed by beta decay to the product P, and then P can decay by neutron emission to an isotope of P, and those are delayed. They are delayed roughly by the half-life of this beta decay here. So if you get your reactor up to subcritical, that is K just slightly less than 1, with your prompt neutrons, you can then use your delayed neutrons to bring the reaction up to critical, that is K equals 1. And those few seconds that it will take for those delayed neutrons to be to appear gives you the time you need for the control rods to come into operation and get into place so that thereafter you maintain a steady flow of neutron production so that you get 1 neutron for every iteration. So that we end up with a design roughly like this. We've got our nuclear fuel rods, we've got our coolant and our moderator, all one and the same thing. The coolant is pumped through, takes heat out, that can be exchanged to produce steam, to drive turbines, to drive generators. We've got our control rods made of cadmium which absorb our neutrons. We're relying on the production of delayed neutrons to stop the whole thing from going supercritical. We just want to keep it critical at K equals 1. And so long as you've got uranium-235 in those fuel rods, then the produced neutrons, having been slowed down by the moderator, the water, can go through this process again, and each iteration they produce energy, and we try to keep n equal to 1, or it becomes k, we call k equal to 1, so that each iteration absorbs a neutron and produces a neutron, and that neutron, having been slowed down, can then hit another uranium-235 and produce and get absorbed, and then produce another neutron that can go through the process again. And that's a nice steady reaction producing energy.